Hello everyone, for today's video we will try to derive the Einstein's field equations. The equation that describes gravity as a geometric property in space-time curvature. As you can see here, this is the Einstein's field equations. Okay, so based from Einstein, gravity is not a force as what we have known from Newton's law, but it is a geometric property in space-time curvature. Okay, so let's try to understand that. Imagine we have a heavenly body here, and this is the space-time curvature. Sabi ni Einstein, the gravity is not a force, but is due to the space-time curvature. Okay, so to derive a field equation describing the curvature of space-time, of course, we need the assumptions first, that the field equations should be tensor equations. Why? Because all laws of physics should be coordinate independent, and the only way to achieve this is to construct them out of tensor quantities. Also, the field equations should relate curvature to matter, and that the field equations should obey the local conservation of energy and momentum. Okay, so ibig sabihin pala to derive the Einstein's field equation, we need to have something like this, a tensor equations that describes the curvature of space-time, and something here that describes matter and energy, or that is the energy momentum tensor. Okay, so we know that the energy momentum tensor is given by T mu nu. And thus, for this curvature right here in the equation, we need to have a tensor equation that has a type 2 tensor. Kasi we can see here that the energy momentum tensor is a type 2 tensor. So, ibig sabihin pala, ang tensor equations dito dapat is a type 2 tensor. Okay, so to describe a curvature tensor, we can refer to the Riemann tensor because Riemann tensor describes curvature. So from Riemann tensor, we know that a Riemann tensor is a type 4 tensor. Pero ang kailangan natin dito is type 2 kasi nga type 2 tong energy momentum tensor. And we can refer to the Ricci tensor or the contraction of Riemann tensor. As you can see here, the Ricci tensor is given by R mu nu, or that is a contraction of the Riemann tensor. Thus, we can say a proportionality between the Ricci tensor with the energy momentum tensor. But there is a problem here, since this equation or this proportionality does not respect our assumption of the local energy momentum conservation, or this just states that the divergence of the energy momentum tensor is 0. So the conservation of energy momentum tensor is given by the covariant derivative of the momentum tensor is 0. Ito yung conservation laws sa general relativity. But since Ricci tensor does not obey this covariant derivative is equal to 0, ibig sabihin, hindi pala siya Ricci tensor lang. Meron pang iba. So, tawagin natin yung Einstein tensor. Since itong proportionality na to ay hindi pwede, dahil ang Ricci tensor does not obey the covariant derivative is equal to 0, let's try to write another type 2 tensor for curvature. That is the Einstein tensor. G mu nu is proportional to the stress energy tensor. Now, this Einstein's tensor, curvature tensor, should obey the covariant derivative of G mu nu should be equal to 0. So now, let's try to find what this Einstein curvature tensor really is. So now, let's go to the differential Bianchi identity for the Riemann tensor, given by the equation from the tensor calculus, differential Bianchi identity, given by this equation, the covariant derivative of the Riemann tensor So this is the differential Bianchi identity of the Riemann tensor. Okay, so to derive from here, let's try to, so ibig sabihin, kapag mayroon tayong nakuha ditong type 2 curvature tensor, that describes our Einstein curvature tensor. So ibig sabihin, tapos na tayo sa pag-derive ng Einstein's field equation. So, ibig sabihin, let's try to find a type 2 tensor. So, first, let's try to multiply this equation by a metric tensor, G alpha mu. And also recalling the property of the Riemann tensor that the indices Riemann tensor alpha beta lambda mu is equal to the negative Riemann tensor alpha beta mu lambda. So, pag pinagpalit natin itong dalawa, that will give us a negative that Riemann tensor. That is a property in the Riemann tensor. Thus, this equation will become, sa baba, this equation will become the metric tensor, G alpha mu, multiplied by the covariant derivative, and the Ricci or the Riemann tensor minus, why minus? Dahil galing dito. Minus the metric tensor plus the metric tensor times the covariant derivative of the Riemann tensor is equal to 0. Okay? So now, due to the metric compatibility, okay, ano yung meaning ng metric compatibility? That states that the laws of special relativity should apply locally. Okay, so in terms of mathematics, that just means that the covariant derivative of the metric tensor should be equal to 0. This is the metric compatibility. Okay, so using this equation, we can now put our metric tensor inside the covariant derivative. Okay? So now, pwede na nating ilagay si metric tensor inside the covariant derivative. So, meron tayong so now, after that, since a metric can raise an index of alpha, so ibig sabihin itong metric na to can raise an index of alpha and replace that alpha into mu sa ating Riemann tensor. Okay? So this equation will become the covariant derivative of the Riemann tensor minus the covariant derivative again of the Riemann tensor plus okay. So in the third term, ang ni-raise natin is the index of the covariant derivative. That will give us the equation right here. Okay, so we can see here there is a contraction from the mu index. That will give us the contraction of the Riemann tensor will result to a Ricci tensor. That will give us the equation of the covariant derivative of the contraction of the Riemann tensor, or that is the Ricci tensor. Plus the covariant derivative of the Riemann tensor is equal to 0. Now again, we can still multiply a metric from this equation. It's called that G beta nu. And again, from the metric compatibility, pwede na agad nating ipasok si metric sa loob ng covariant derivative. So, ibig sabihin pala nun, we can have the equation minus the covariant derivative as we can see here, again, in this equation, we can raise the beta index into a new index in the Riemann or the Ricci tensor. Thus, this will give us the covariant derivative of the Ricci tensor minus the covariant derivative, the Ricci tensor R nu lambda, plus the covariant derivative of the Riemann tensor. Again, there should be a metric here. So, meron dapat ditong metric. Okay, so now this should be equal to 0. So, finally, we can see that there is again a contraction of the Ricci tensor right here in the new index. So, that will give us a Ricci scalar. Okay, also, we can use again the property of the Riemann tensor here that states that the R alpha beta nu lambda is equal to the negative of R beta alpha nu lambda. That is again a property of the Riemann tensor. Pinag-swap natin to, we will have a negative sign of the Riemann tensor. Okay, so this is a property of a Riemann property of Riemann tensor. So finally, this equation will become the covariant derivative of the Ricci scalar R minus the covariant derivative of the Ricci tensor R nu lambda minus the covariant derivative. Again, since this metric, okay, can raise the index of beta to nu in our Riemann tensor, this will become the covariant derivative of the Ricci tensor. Okay? So finally, from this equation, we can express this covariant derivative with an upper index as the covariant derivative of alpha is equal to the metric tensor alpha rho and the covariant derivative of rho. So finally, this equation will become again, since this is metric compatibility, pwede ko na agad ipasok sa loob si metric. Okay, so meron tayo ditong covariant derivative of rho G alpha rho multiplied by the Ricci tensor is equal to 0. Saan to galing? From this equation. So ito, ginawa natin ganito, thus meron tayo ganito. Okay, so finally, we have our equation from the Bianchi identity. This equation will become the covariant derivative of the Ricci scalar minus the covariant derivative of the Ricci tensor nu lambda minus the covariant derivative of the Ricci tensor rho lambda is equal to 0. But since this is just a dummy index rho, we can write or we can replace our rho index into the nu index. Thus, we have the covariant derivative, the Ricci scalar minus covariant derivative of the Ricci tensor minus covariant derivative of the Ricci tensor is equal to 0. Thus, ito ay magiging equal sa 2. Okay, so meron kang equal to 0. So now again, from this equation, we can again multiply a metric tensor mu lambda. So sa equation na to, we can again multiply a metric tensor mu lambda. So multiplying a metric tensor and again applying the metric compatibility right here. The metric compatibility. Again, pwede na nating irektang ipasok si metric tensor inside the covariant derivative. That will give us the covariant derivative of the metric tensor g mu lambda and the Ricci scalar minus twice the covariant derivative nu g mu lambda multiplied by the Ricci tensor is equal to 0. So again, we can see right here that this metric raises the lambda index into a mu index. So finally, we can write this equation as the covariant derivative g mu lambda r minus twice mu r Again, this is nu pala. This is nu. Okay. Okay, so R mu nu is equal to 0. So finally, multiplying this equation to negative 1/2, we can write, and also, pwede nating ilabas si covariant derivative. Again, papalitan natin si lambda into nu index. Again, bakit pwedeng gawin yon? Dahil that is a dummy index. Okay, so finally, we will have the equation of the covariant derivative of the Ricci tensor R mu nu minus 1/2 the metric tensor G mu nu multiplied by the Ricci scalar R is equal to 0. So this equation represents the curvature tensor. Again, from the proportionality equation from above right here, proportionality equation, ito, we can write the Einstein curvature tensor G mu nu proportionality to the stress energy tensor T mu nu. Thus, to make this equality, meron tayong G mu nu is equal to some proportionality constant K is equal times the stress energy tensor. Thus, ibig sabihin pala, this Einstein's curvature tensor is also equal to, thus, the Einstein's curvature tensor G mu nu is equal to R mu nu minus 1/2 G mu nu multiplied by R. Okay, again, this equation satisfies the conservation law that is needed for the stress energy tensor. Again, ito kasi bawal siya maging katulad nito, no? Kaya naghanap tayo ng bagong curvature tensor that is called the Einstein curvature tensor. Thus, we now have the Einstein's field equation. The R, or dito natin lagay, the R mu nu minus 1/2 G mu nu, or G mu nu, R plus some lambda G mu nu is equal to constant times the stress energy tensor. So, saan to galing? This constant right here is nilagay ni Albert Einstein, pero tinawag niya itong his greatest blunder. Pero ngayon, meron na itong nakikitang meaning nito. This serves as the factor for the dark energy sa cosmology. Okay? So, ibig sabihin pala, this is the Einstein's field equation. Again, this term right here doesn't affect this covariant derivative, since this is metric tensor and this is just some constant lambda. Okay, so kahit ano man yun, ang covariant derivative pa rin niya ay 0. Thus, we have derived the Einstein's field equation, or pwede rin siya in terms of the lower index. Either way, that is our Einstein's field equation. Okay? So that's all for the derivation of the Einstein's field equation. Thank you for watching.